discrete probability, because you need to study it, okay? And we study it using combinatorics, basically combinatorics, that's it. We no longer see continuous probability, that means integration, differentiation, all out. This is a reason why you study probability. You have two sorts. One is one I randomly make up some bullshit name, and then you have this, and another one is a big sort, okay? And you have this. Which one is better? How do you calculate? You use probability. I'm now telling you they use uniform distribution, which you can calculate. So we will call our thing sample space. It's the same as domain of disclosure in logic. We consider something we talk about, we call it sample space, and we call it omega, and we assume it's non-empty. Why? Because if we talk about nothing, then nothing to discuss. Okay, that's it. Trivial. This is called non-triviality. That means what? We don't talk about empty set. And let's say you have a coin. You toss a coin. You can either get head or tail. So if you toss it one time, so it's H or T, trivial, right? If you toss it two times, HH, HT, TH, TT, two times, right? And this is also what? This is have two outcome. You choose two to the power 2, right? What about this? This is you toss a coin 3 times, you can get HHH, HHT, HDH, blah, 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 so on. This is what? You have an outcome of 2, you do it 3 times, so it's a 3 branch 3 times. Every time you branch, you have 2 branches, so 2 to the power 3, combinatorics, okay? And then what is an event? Event is something you care, we care. For example, I want 3 head, then this is an event. If I said, I want what? I want 3 head or 3 tail, that means event is these 2 together. Important, I'm saying a subset is an event. So if 3 head or 3 tail, my event is 3 head or 3 tail, then these 2 together is an event. And this is a subset of this big set. Okay? If I'm saying less than 3 head, then this is okay, 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 this is okay. Then all of these are less than 3 heads. So these are event. So it's a subset. That's it. So this is what I mean. Event is a subset of my sample space. And on the other hand, if this is smaller than sample space, then I can say all the event, that means all possible events you can think of, give me sample space. And what is classical probability? The cardinality of event divided by the cardinality of sample space. And since cardinality related to combinatorics, that's why this is combinatorics. So combinatorics is what? How big is a set? What is probability? We calculate how big is 2 sets and divide them. That's it. So therefore, probability is just combinatorics in disguise. That's why I said one stone kill 2 birds. You study combinatorics, you automatically know many things in probability. You just don't know the name. For example, this is name, this is name, this is name. And because we cannot divide by 0, so that's why we have this. Important. E can be empty set. For example, I can say, I toss a coin 3 times. I'm asking, I have 4 heads. Impossible. So empty set. And also, omega can be infinity. For example, here are crazy things. These are not classical probability. I'm just telling you. Suppose in my mind, now I have a natural number starting from 0 to infinity. I just randomly choose a natural number. And you want to guess what I'm choosing in my mind. Then the sample space will be the size of natural number, which is countably infinite. That means infinite. You are going to guess one number a time, so E is a singleton. That means one thing. So the probability of you guessing me the number correctly will be 1 divided by infinity, which is 0, meaning that it's impossible for you to guess the number correctly. But if you repeat this, let's say 200 times, probably one of them you will get it right. Then here's a contradiction. Isn't the chance is 0? How come 0 times 200 is something equal to 1? I will talk about it later. Okay, you know something called D&D. If you don't know, it doesn't matter. So again, I don't spell D-I-C-E. I spell this because this stronger impression in your brain. So therefore, you will remember this. So 1D4 means you toss a 4-sided dice 1 time. Then omega 1D4 is output is 1, 2, 3, 4. Okay. And then if my event, I call E1, is less than or equal to 3, that means it's 1, 2, 3. Then what's the probability? How big is this event and how big is my sample space? Well, easy, right? Just 0.75. And then if my event is, it is an even number, then 2, 4. Yeah. And then the size of this set is 2. 2 divided by 4, half. Yeah. And then if my event is larger than 0, well, all the numbers here are larger than 0. So, of course, the probability is 1. And then if my event is less than -2, none of the number is a negative, so empty set, so 0. And then 2d4, I toss this 2 times, and I draw like this. This is Cartesian product, and you always need to draw this kind of picture because we will use this to talk about this. So you draw it like this. It's a matrix. First number is I, second number is j. This means what? First outcome is 2, second outcome is 1. First outcome is 3, second outcome is 3. First outcome is 4, second outcome is 4. Drawing like this has a meaning, okay? Then these are all the possible way. How many? 16. Now, if I toss 2 times, and I want the sum larger than 6, this is a very typical thing in D&D, okay? If you don't know what is D&D, doesn't matter, okay? You just think of this as a math. You know what is D&D, you have a happy childhood. So you count I plus j equal to larger than 6. So 3, 3 is 6. 3, 4 is larger than 6. 4, 3 larger than 6. 4, 4 larger than 6. So these are okay. So you count how many of them? 4. 4 divided by 16. 1/4. Yeah. And what about this? I smaller than j. So you find all the things that I smaller than j. E will be this. Okay. Then you just write it down. Then it is 0.7375. Okay. What about I equal j plus 1? I equal j plus 1. So that means what? I equal j plus 1. I equal j plus 1. I equal j plus 1. So only 3 of them. So 3 over 16. Last one is funny. I plus j is a prime number. So you need to really find, is this prime number? 1, 1 is 2. 2 is prime number. Okay. 1 plus 2 is 3. Okay. 1 plus 3 is 4. It's not prime number. Not okay. This is 5. 5 is prime number. Okay. 2 plus 1 is 3. Prime number. Okay. This is not prime number. 5 is okay. 6 is not prime number. 4 is not prime number. 5 is prime number. 6 is not prime number. 7 is prime number. 5 is prime number. This is not prime number. This is prime number. So have this. And then we have 3 sentences, actually 4 sentences of probability axiom. This one is trivial. We don't talk about empty thing. Otherwise, nothing to discuss. All probability is larger than 0 or equal to 0. Probability of the sample space, that means all the things together have 1. This one is funny. What the heck? Again, this is just fancy name. This is called sigma algebra. It says that the probability of a OR event is just the sum. That's it. So the idea is this become summation. This is what? This is this in capital letter. So therefore, people call it sigma algebra. That's the reason why they call it like this. And they are disjoint. And here's the thing. This is revision. I have A, B. If they are disjoint, then A intersect B is empty. That means they share nothing. In combinatorics, what's that? It's exclusion-inclusion principle. In probability, what's that? We call it mutually exclusion. That means what? This is one stone kill 3 birds. They are the same thing. It's just different name. This 3 axiom, I have the 0. That means we don't talk about nothing. Together, give us this. You may think these are axiom. These are not axiom. For example, probability is smaller than 1. This is not axiom. I just said it's equal to 1 and larger than 0. These two give us this. Why? E is always subset of this. By subset, we know the size of E is smaller than the size of omega. And then what? So this, I put a bar here. Here, I put the probability symbol here. Then this guy, by axiom 2, is 1. So this guy is 1. This guy, I just said axiom is larger than 0, so it will be what? Something 0. And I get what? PE between 0 and 1. You see, I didn't say this in the beginning. I just said probability of event is larger than 0. I only say this part. I didn't say this part. This part is induced by what? Set theory, combinatorics or set theory, and this is what? Definition of probability on sample space. So this thing is not coming from probability. It's coming from something else. So that's why you have this. And also you have this. Why? Because what is empty set? Empty set means the complement of the everything. So you do the set theory of complement. That means subtraction. So you have 1 subtract 1. That means you have 0. And also you have this. Well, it's the same thing I just discussed. I give you all the proof. Okay. But anyway, we don't talk about proof too much in this part. You have proof in the set theory, but not here. Okay. And now we have even more stuff. First of all, you see I draw 2d6 for like this. Later I will draw 3d6 in a 3d thing. This has a meaning. But now let's go back to here. So it's complement. It's just set theory. Everything subtract the thing you discuss is the complement. Nothing new. and the probability is just one subtract because this corresponds to everything. That's it. So suppose I have this, toss a coin twice, HH, HT, TH, TT. Now I want at least one H. What's the first way to do it? Brute force everything. But you can also say I use complement. Then I find the opposite. At least one H, the opposite is always T, so 2T. And then I do one subtract. They are the same, okay? So one subtract this number, give me this number. The idea of this example is not, oh, these are so easy, so dumb, so simple. Yeah, the idea of this is that sometimes when you count things, count directly is very difficult, so you count the opposite and then subtract. This is the same idea as if you count X is Y, you count Y and by bijection. These are all techniques you can use to count stuff. So EC is useful when E is tedious. That's what I said. Here's another example. 3D6, I count 3 6-sided die 3 times. So how do you draw? Well, if you count it 2 times, you could draw a table like this. If you count it 3 times, you draw a 3D table. This is called 3D table, or you want a fancy name, right? This is called tensor. You don't need to know what the heck is this. I now want I plus j plus k smaller than 18. What the heck? So you look for all the I plus j plus k smaller than 18. This part is a little bit difficult. So you find the line that I plus j plus k smaller than 18. It will be what? This is a 3D thing, right? Okay, this is a 3D thing, right? Let me go back to 2D to give you the idea. So I have a 2D thing. If I want I plus j equal to 6, that means what? I want something here. So I plus j is 6, 2, 4 is 6, 3, 3 is 6, 4, 2 is 6. So I want this line. I want some line here. Then now 3D is the same. I want a plane cut through this box. Everything on this plane are all the I plus j plus k equal to some number. That's how you visualize this. This is a little bit complicated because you need to have 3D vision. So we do the complement. What's the complement? What's the opposite of this? The opposite is this is larger or equal. You cannot go larger than 18, so you can only have 18. So you count how many ways you can sum to 18. There's only one way. So that's how you get this number. Yeah. So that's the what? Usefulness of this thing. These are stupid. Now you see this is not stupid. Okay? And another name. Again, name. Mutually exclusive. That means what? Disjoint. What's disjoint? Disjoint means A and B are empty set. Okay? And then what? This is set theory. This is probability. What about combinatorics? It's sum rule. What is sum rule? Inclusion-exclusion principle without a subtraction. So therefore, the 3 things are the same thing. It's just different name. And probability given name cannot occur at the same time. Mutually exclusive come from complement. And complement do not go back like this. These are different. So here is an example. Suppose EF like this. EF are mutually exclusive because disjoint. E and F, nothing. EG also mutually exclusive. E and G share nothing. E is 1, G is 3. They don't share common thing. FG are not mutually exclusive. F and G both share what? G, that is 3. Is F the complement of E? Yes. Is G the complement of E? No, because the complement of E is 2, 3. It's F, it's not G. So this is, again, set theory, nothing new. And these are what? Probability version of set theory, sum rule, and combinatorics. That's why I said, one stone kill 2 birds. You know combinatorics, you know probability automatically by just adding this symbol. Okay, and then you also have this. Okay, this is sum rule. What? Probability version. Okay, this is inclusion-exclusion. This sum rule. This is inclusion-exclusion principle. Inclusion-exclusion principle in combinatorics is like 2 bar. In probability, you replace this 2 bar by a p. It's the same thing. And then you can also draw this kind of Venn diagram. Not going to repeat it. It's the same thing. Therefore, you also have this. So again, omega sample space 1, 2, 3, 4, 5. You can think of this as tossing a 6-sided die. E1 is 1, E2 is 2, 3, E3 is 3, 4, E4 is 4, 5, 6, E5 is 6. And then I want to count what is the probability of E1, E2, E3, E4, E5. If you do the OR of all this, it gives you back 1, 2, 3, 4, 5, 6. So of course it is the sample space. This is what? This is just me showing that you can do this by the sum rule and inclusion-exclusion principle to get the same result, which is nothing new. It's the same as set theory. It's the same as combinatorics. So I will skip this. Probability is just combinatorics and set theory again with this new thing. You have 2 sets, Find the number, divide them, that's probability. And this is called classical probability. And you have 3 axioms. And the only thing that is not so trivial is the last one, is union becomes sum. This is sigma. Notation is sigma. So this is called sigma additivity. These two are just set theory combinatorics, nothing new. The real deal comes from here. Yeah. See you next week.